Yeah. All right. Welcome everyone to today's ICON seminar. Our speaker today is Professor Ningshi Yao from George Mason University. And Ningshi got her PhD degree from Georgia Tech in 2020. And before that, he received his bachelor's degree in science from Zhejiang University. So he graduated from the same school for undergrad. And before joining George Mason, Ningshi was a postdoc at Georgia Tech as well. And today, her research is about cyber physical systems, physical theory, and linear line interaction. And she developed a student and also some wonderful robots here. So this might be one of the first few times we have live demos during ICON seminar. So thank you so much for taking the efforts and time to make this happen. So today, Ningshi will give a talk about dynamics and control of lighter than air autonomous blimps, design, development, and deployment. Let's welcome Ningshi. Thank you.
Yeah, thank you so much for having me here. So I had the great conversations with Purdue faculties and especially ICON faculties and also students. So hopefully I can return your favor and also give you a good introduction and also share about our work on miniature robotic blimps. And we do have one session for live demo. So you will see what the blimp actually fly. So if my controller works. So before we talk about blimps, I just want to give you a big picture about what I do, in general, research-wise. So I'm leading the child lab at George Mason. So it's a control, intelligent autonomy, and also optimization lab. So I have a broad interest. So theoretical-wise, I mainly work on cyber-physical systems. Specifically, I work on the real-time scheduling, real-time resource allocation, and control co-design together. So one example is actually this traffic intersection, right? So you need to allocate which vehicle can use this shared resource, which is the intersection first, and also design the speed and also the corresponding control for the car. And this one is another interest of mine. So we study also use control theory and also dynamic system to try to study how human and robot interact with each other. For this specific scenario, we're trying to study how human and the robot will mutually adapt to each other. Then using control theory, we want to study under what condition we will have this limit cycle. So I try to adapt, you will also try to adapt, and we cannot converge, right? So that's another interest. And this bottom left was a very exciting project. We recently got an NIH grant, so which will allow us to build this artificial muscle-driven robotic eye to actually help us to study humans' ocular motion and also try to study the strabismus, which is one specific cross-eye disease that's affecting more than 10 million of Americans. Actually, it's a big number. And then this is actually last but not the least is today's show. I'm going to focus on talking about the indoor robotic blimps, how we design, deploy, and also design, also control corresponding to achieve autonomy on it, right? So this is my student trying in our lab, try to capture and also score autonomously. So, and it scored out of multiple failure. I picked the one that's successful. Okay. It's a joke. We actually success a lot of time. Okay, so then to give you a quick introduction about airship, I think this is actually blocking my title. So if I click, okay. So airship or blimps start from outdoor. So this picture is actually showing in 1930s. They launched the first actually outdoor airship that achieved the cross-Atlantic mission. So it flies across Atlantic Ocean. But then the end is actually they abandoned this rule as an air transportation because they used nitrogen at that time. And it eventually blew up, caused some tragic accident, right? So later, helium was funded as a much safer gas, lighter than air gas. So now the blimps, outdoor airship or blimps, we use indoor or use helium as the lifting gas. So then what is the blimp that we use? I think I somehow have some problem with clicker. Yeah, so the blimp we use, you can think about we have a helium inflated balloon, right? So, and this size is about exactly that size that we will show later. So you inflate this envelope with helium, and we try to attach microtronic component underneath it. So this is a bottom view. So what we do here is we put a central controller here, which is a Raspberry Pi Zero. And on the two side, we just put two propeller on each side. So one propeller and also motor on each side. So each propeller is attached with a servo motor. So then we can actually also change the direction of where the propeller is facing. So what we can achieve is, because helium will naturally provide the lift, and then using this propeller, we can achieve differential drive. If you actually tilt the servo motor by 90 degrees, we can fly up and down, right? So this is very trivial. And also you can have a different design of gondola. So this is slightly more complicated design. So we have two propeller horizontal taking care of up and down. And also this full propeller will actually achieve the omnidirectional motion, right? So then we can move in this direction and also in this direction. And also you can be creative. You can design your own gondola, which is a microtronic part attached beneath it. You can have different design. And then generally, if we have a helium inflated balloon plus some microtronic component, we can actually easily make a blimp. All right, so then you may ask why we need a blimp, especially miniature indoor blimp, right? So I will actually try to sell this idea very quickly. So the benefit of using indoor robotic blimp is, first of all, it's small in its size. And the major benefit it gives us compared to like a multi-copter drones or the fixed wing airplane is that because helium provides the main lift, so you don't need to waste the battery power to just flying, right? So then because all the power is used to move the blimp around. So then for one blimp, if you use a decent size of battery, so we can achieve up to 3 hours flight time per battery charge, right? But if you use indoor drones, maybe 15 to 20 minutes, the bigger outdoor drones up to 1 hour, that's the maximum, right? So that's definitely the first benefit, because if we want to think about for indoor tasks that need long duration, right? So for example, I do human robot interaction experiment. So if I need to collect continuous human data, so Blimp is actually an ideal platform. Without any interruption, I can collect the human data. Another obvious advantage is that it's more friendly to human, right? So I will show you this video. So imagine a drone doing this to you, right? Even it's small, even it's protected. I won't allow them to do this to me. But yeah, it's hilarious. When we shoot this video, the girl is actually enjoyed it. So because the balloon is naturally cushioned, soft, so then human will actually feel safe when it's next to it, right? So when the human is next to the blimp, then we'll actually have like an elementary kid coming into our lab when we do demo, they naturally want to play with it. So this is friendly to human. Then naturally, the application we can use the miniature robotic blimp to do is, first of all, we can use this as an indoor surveillance tool platform, right? So to do indoor monitoring. So if you think about construction site, we have this routine monitoring task, especially at height. Then Blimp is the ideal platform to do that, because Quadrotor, again, it's unsafe to use indoor. Or we can actually create this experimental illusion platform. So this is actually what's being done at the Naval Research Lab. They launch more than 30 blimps together in their lab facility, let them bump to each other just to study the swarm behavior of multiple blimps. And also, it's safe to let them bump to each other. And we actually want to study this kind of behavior. So all those are benefits. What are the difficulties? The major difficulty is that if we want to make this lighter than air, then helium won't, and also because of the volume, how small the blimp is, it have very limited payload, right? So this guy that we are going to show only have 120 grams of payload. So then everything, if we want everything on board, that's actually a big challenge. Okay, and then before I tell you how we are able to kind of bypass it in lab, or we can actually try to solve this problem, let's fly the blimp first, so then the audience can see what the blimp looks like. So today we're bringing two of our development. The first one is this guy, which is propeller-driven. So from my previous slide, I already show how it can fly. So my student now is just manually flying it. Yeah, so we also have a onboard camera. We can fly are you able to try the autonomy on it?
Yeah.
Okay, we also have a like autonomous functionality on it. So what we will do is it's able to recognize human. We have a lot of human in this environment, so it may be confused. So he raised up his hand, so Blimp should be able to fly towards to him. And this is now fully autonomous. Okay, good job. Yeah, so it's enabled by actually onboard controller, and the sensor is the onboard camera.
Do you want to take a risk and have somebody raise their hand in the audience?
Yeah, or maybe just one. Yeah, because we haven't figured out how to.
Maybe stand up.
Yeah. Okay.
Just raise it up a little bit.
Oh, just one hand. Yes, steady. You need to turn. You need to turn around.
It will try to find it.
Oh, okay. So you have a searching algorithm on board as well.
Yeah. Which is not fully tested, but.
Okay.
I'll just turn it around.
Okay. Yeah, it's rotating too fast.
Is seeing the person in the.
Okay, let me move on to the another slide.
There we go.
Okay, yeah.
Oh, yeah,
Yeah,
high five.
right. High five, yeah. So then, let's launch the next one. So we can let this guy hang around. So the second one is actually the like more novel locomotion that we try to do. So instead of using propeller, we actually do this flapping wing driven blimp. So it actually looks more like a sea creature. So the flapping wing will allow it to fly up and down. Do you want me to turn it off, turn it around? And also it's easy to safe for it to bump. So let's fly to the audience.
The only actuator is the flap?
Yeah. It's a servo motor, so we flap it. And then the tail will actually be able to control the pitch angle. So if you try tail up. Yeah, feel free to like gently push it. It's okay. And this guy is hanging around. And then if the tail actually goes down, because tail actually can change the CG, so center of gravity. So this is how we are able to change the pitch angle of the flappy. So then we can actually make it fly up or fly down. Okay, so I think that's it. Yeah, thanks. So this is my PhD student, Youjang Godan. So like he mainly like take the lead on developing and also work on the Blimp project in my lab. Yeah, so thanks Youjang for preparing the demo. Yeah, you did a good job. Okay, so then actually let's talk about how we are able to achieve all of them, right? So as I said, the first difficulty we need to overcome, also one of the major difficulties is like we need to now think about the engineering design constraint, right? So like the payload is larger than constraints. So one way to do this is that if we want to use this in lab, so one configuration we can have is we can rely on the external like localization system and also ground station to help us to do the computation. So the in-lab setup, which has a first step, we actually can put the tracking marker on top of an envelope and then use motion capturing system to measure the accurate location and the pose of the blimp, right? Then the mocap will directly transmit the localization information to a ground station, and then we use it to compute like the control command correspondingly. Then the control command will be wireless transmitted to the blimp, and the blimp just execute. Right, so this is one way because we offload some major part of the sensing and also computation to the ground, right? So then Blimp just need to carry the actuator and also a little bit like a communication module to do it. Then this one is actually a smaller blimp we use. So the payload of this is just 80 grams. So we are able to do this everything in 80 grams. But then this design have actually some assumptions, right? So first of all, off-board computation, which is a limitation, right? Limit us to deploy it outside of lab, external localization and sensing. And also, like, we assume we have minimal disturbance. So disturbance here is mainly talking about the wind, right? So the blimp is very light, so it will actually suffer a lot if we have a wind or if the AC is strong. So I will talk about like actually later our work, how we are able, how we try to relax all those assumptions, right? But then if we do this indoor, so then like we can actually fully use the blimp dynamics and also try to design a good controller. So this slide generally actually shows the general 6 degree of freedom dynamics, right? And also this is dynamic equation. So then like a position, pose plus its corresponding velocity will have 12 state variable. And then just roughly speaking, so this two equation will actually be able to model the full dynamic of blimp, right? So it's very powerful. It's able to describe what the blimp do. But actually in reality, if we want to use those equations, the challenge is that we need to identify all the parameters, which is very hard to do. So then in order to solve this problem, so and also another problem is that the blimp will also like have this external disturbance, which I denote this as a capital F, capital M. So here, like because of the environment, sometimes capital F and capital M, which is the external force and also momentum, will be the dominant force, which will making the control very hard to do, right? Then like in order to actually have a better, like to make the design of the controller easier, so the first step we do is actually we use the three motion primitives. So the blimp, because of how we design the gondola, it's constrained to only have this three motion, which is forward, backward. So if I replay this animation forward, backward, up and down, and also changing the heading direction, right? So given that is like those motion primitives, and also we assume those motions are actually decoupled, which is not true. So we will see this right in the next slide, right? So they are actually coupled. For example, forward and like roll, not roll, yaw is definitely coupled together. So, but then if we assume those are decoupled, then the nonlinear full dynamic can be simplified just a second order dynamics, and also they are separated, right? So because this is second order, so if we after first, like for now we ignore this external force, then we can just easily use a PID controller to stabilize the system and also control it to a reference. Okay, so then this is now our simplified linear model. So easy enough because then it's just mass, which can be directly measured, right? And then we can actually go ahead and do the system identification. So I'm showing 3 transfer functions. So the first transfer function is actually showing the, I think, forward backward motion, right? So you can see it was supposed to be second order, but after after we get the output response to a step input, we actually can only identify this as a fourth order. And that's because of the coupling of this motion with other motion, right? But with this transfer function, and the second one is like the changing of attitude, so up and down. And we can see we actually have 2 different dynamics. This is because the efficiency of moving up and moving down are different because you have a big chunk of envelope blocking the airflow. So flying up is harder than flying down, right? Because the wing jet is actually blocked majorly by the envelope. So we actually deal with this by actually separating this as 2 different transfer functions. The last one is the changing the heading angle, right? So then we can see, because of like based on this identified transfer function, they are either marginally stable or unstable. So we actually need a controller to stabilize it. And then like as a very trivial first step, right? So we just grab this transfer function and design the PID controller correspondingly, right? So then let's see how it works. So the first one is we try to test this in lab, try to test the altitude controller. So we have a reference height, and then it's able to quickly converge to that. And if you add a big disturbance, right, it can also come back to this reference height. So then that means the height controller kind of sort of work. Yeah, sorry, I fast forward this. So let me actually show you the yaw controller. Yeah, and this is the controlling the heading angle. So the blimp was supposed to look at 90°, which is projected here, right? And same thing, it can actually converge to this 90° reference. And combining the altitude, the forward, and also the yaw controller together, we can actually achieve a waypoint controller, right? So we just assign a bunch of waypoint, which is actually 4 corners of this space. But then that blimp can actually follow this trajectory, try to visit the 4 corner and then loop around, right? So this is like the basic functionality. And with this, we can already start to do our first application. So this is truly my work. So like a long time ago, well, I still have a short hair. So we actually use this identified model and also PID controller to do a quick human robot interaction demonstration, which is actually used in our demo today. So it's trying to identify a human face. And then as I walk around, what it tried to do is just to log this detected face at the center of the image frame, right? So if I walk around, it will try to follow me using the yaw controller. And if I kneel down, which will be, yeah, so I'm about to kneel down, it's able to adjust the height. But if I stand up, it will actually stand up. If I suddenly step too close to it, it will try to maintain a polite distance from the human, right? And those are the collected data from like our object track system, just to use this as a ground truth, right? And then build on top of that, I want more like a bi-directional interaction. So what we do is instead of just detecting face, we also created 2 motion, like a hand gesture, which is horizontal motion, just wave your hand horizontally or vertically, right? And it's enabled by just a SSD, which is a 1 deep neural network to do object detection. And then Blimp is able to recognize it. If we wave this horizontally, it's going to spin. And also we put a small LED light to say, oh, I got your point, right? So I'm about to do the corresponding action, right? So then we use this to actually collect the human data to study whether there's a bi-directional feedback, right? So having this small LED will help with the interaction or not. So this is some experiment we did. Okay, so like simple and efficient, right? So the PID controller. But then if we think about, if I want more precise control, here is a problem. If you watch this video, right, you probably catch it when we are doing the demo previously, so we can rewatch this again. If he start, right, you see this big pitch oscillation, right? That's because if at the beginning, I'm trying to move from the static stage to be suddenly I need to fly fast. So this is actually because we put everything heavy beneath, right? So it's like a pendulum model, and then you quickly apply a giant force to it, and then it will start oscillating, right? And also if I immediately stop the force, so because this is a pendulum, it will actually damp down the oscillation. But the bad thing is because we have this active feedback, so it's always trying to correct it, right? So then it's getting worse and worse. So we have this swing oscillation happening during our experiment. And also this pitch oscillation can also be caused by the wavy image. So actually sometimes the image measurement is kind of like a noisy, so that it actually mess up with the image or like with the measurement, or sometimes it's directly incorrect measurement. So will cause this swing oscillation, right? So then we also want to design a controller to see whether we can reduce this swing oscillation, because this makes the flight less stable. Okay, so this is a lot of equation. So I will quickly explain it. So then what we do is we try to actually look into actually the state space model about this, just modeling this 1D like swing oscillation, pitch oscillation, but it's still coupled with the translational oscillation. So it actually depends on how fast you are trying to fly forward, right? So which makes sense. So then this first equation, so the blue variable is trying to actually, is denoting the speed, right? So the translational speed. The green one is actually the pitch angle and also pitch oscillation. And then the orange is the control I have, right? So then my point of showing this, and also is this is nonlinear, and all those black are just, you can view this as a constant parameter where we can identify or we can preset a set point. So then by looking at this equation, the point I want to make, this is nonlinear. This is coupled and also this is under actuated, right? So because I have a full state, I only have one, I only have two control authorization to compensate for that. Okay, and then the strategy we try to solve this problem is that actually we use the inner and also outer loop control strategy, which is also like a very standard way of doing control, right? So what we do is actually, because the pitching is kind of a faster dynamics, and then speed is a slower dynamics, right? So we try to use the inner loop to damp down the pitching, and while the outer loop try to make it constant speed. So then if we think about like so we try to first compute the equilibrium, right? So what is also we call this operation point, right? So then we find out if the blimp fly as a constant speed, and because there is a displacement of CG and also the drag force. So instead of flying completely horizontal, it actually will pitch up a little bit, because like it created a torque to compensate the torque created by the damping, the air drag. So then corresponding to each constant velocity, there is a constant force equilibrium, there is another constant pitch angle, right? So then our inner loop controller, so then this is the inner and outer loop structure. The inner loop controller will assume we have a constant speed, and then try to design a controller. So we do actually a forward pass by using this equation to compute what is the corresponding force corresponding to this reference pitch angle, and then feed this to like the plant, right? Then we also add a feedback pass, try to just compensate any disturbance, right? So then this inner loop will make sure, actually, if I have a reference or operation pitch angle, it's able to take care of that. So you can fly stably, maintain this pitch angle. And then outer loop is going to actually make sure we have a constant speed, forward speed, because each speed, forward speed will correspond to one pitch angle. Okay, and this is the structure we use. And then we can see how the result will be. So now it's actually more stable, and wait and see. This is my colleague Qiu Yang. He actually tried to increase, like introduce a disturbance, and then you can quickly reduce the damping, right? And also it's very constant flight, right? So it's slow, but just steady. Okay. And if we combine the swing oscillation reduction controller with the waypoint controller, now we can actually achieve like very stable flight, right? So this is again a waypoint controller. And then this, let me see. This is actually the corresponding trajectory we can. So you can see it can actually try to revisit this like a predefined trajectory, and also it's almost overlapping, but it's actually try to decrease the height and revisit, so scan through this field, right? So then what it can do, right? So I can achieve like a good precise control, what it can do. So application of this is that now we can use blimp to mimic underwater vehicle, right? Because it has similar dynamics, it can be easily blown away by wind, like the same way the ocean current can blow away an underwater robot, right? So like we use this as an experimental illusion platform just to allow us to test the algorithm before we actually go ahead and launch an underwater vehicle in the ocean, right? So if your software does not work, that's actually a waste of time, right? And also effort. So this video is showing, like in our lab at Georgia Tech, which like we can actually put like the light in, create a light field, and then we use the blimp, we put the light sensor on it. So we can actually collect at each point, collect the intensity of the light, right? And then the algorithm at that time, my colleagues was testing is just using those sparse measurement of light. So he used one specific method called kriging algorithm that is able to allow him to reconstruct the whole light field, right? So then you can see this is actually the center of the light, which is matching the location of the light we put here. So, and this is actually kind of like a reconstructed light field, right? So you can think about this is underwater vehicle, like a going into the ocean, take a measurement of like maybe pollution or right, so chemical leaking, and then we're trying to remap how the field looks like. Okay, and this is so far I introduced the in-lab application, right? So then the next part is what if we want to move it out of lab? Okay, and this video is showing a blimp competition. So I slightly I increased this a lot, right? So this is out of lab in an adversary scenario. Like then I will also tell you like everything need to be on board. Okay, so and this is played at the GMU, and also you see the flappy here, right? Okay, so let's so this competition is actually a competition George Mason has been playing actually more than 6 years. So I have joined this competition for more than 3 years. So this is called the Defend the Republic blimp competition. So you can think about this as a 3D version of air soccer or 3D version, like a robotic version of Quidditch, right? So what we do is we have 3 goals on one side, 3 goals on the other side. We have blue team versus red team, right? So and those colorful like green and purple balls are just like the soccer ball. Like blimp need to autonomous capturing them and also score them, right? So the competition is played by a lot of universities, right? So like all those are the list. So the rule of the competition is each game is 30 minutes. It's kind of long. That's like 60 minutes. So 30 minutes each half. So each half we need to like during the halftime we need to swap side, right? So then it's fair. So you attack this side for the first half, then the next half you attack this side. And also you defend your side exactly like a soccer, right? So then for every 5 minutes, only the first 30 seconds allow manual control. And also only one blimp can be controlled. All the others still need to be autonomous running. And then the rest of 4 minutes and a half, it need to be fully autonomous, right? People just go, leave the field, right? Hands off from the controller, just let the blimp play. And then we also try to encourage the fully autonomous mode. So then also how we win the competition is at 1 point per manual score, 10 points for fully autonomous, right? So fully autonomous actually weighted a lot more. Okay, and then this competition is like sponsored by Office of Naval Research Lab. And I just want to emphasize, this whole thing is not about competition. It's about research, right? We're just using this platform as our annual review meeting. We want to actually test in the real field our development, right? Instead of like just having the fun in a competition. It's not that fun. It's very stressful. But this is about research. So what research question we're trying to do? It's actually exactly relaxing all the assumptions I had previously. So because it's out of field, right? So then like the requirement is that no off-board competition. Everything needs to be on board. And also definitely no external localization, right? No mocap system. It's in our basketball arena. So, and also there is going to be like wind gust and also opponent team's defense action, bumping action, adversary, right? So then how are we able to do that? And also we have again a design constraint, which is the total payload. Now everything on board need to be less than 800 grams, which is kind of challenging because if you consider battery, everything. Okay, and then, so that means, this means crappy computation, crappy communication, and also crappy control, maybe, right? So you cannot have perfect anything, right? Before you have like a crappy everything, because you eventually want it to fly. Okay, so then before I talk about like how we do that, just want to quickly report the George Mason team's results. So I co-lead George Mason team with another 2 colleagues of mine. So Dr. Cameron Nalari from ECE. So Dr. Dago Shashika from ME department. So it's a team, and we have a big team of students to working on this together. So what I joined in 2023. So we actually did very well here, right? And also highlight. So here we play the first home game at Mason, and this is the final score. We did a lot. And then because we were able to achieve a lot, so then we want to pivot, right? We want to force ourselves to create new things. So instead of using the same agent, play again. So we may massively changed our design. So introduce Flappy, which is so cute to watch, but then it's very hard to control. Okay, and then you can see, right, we have our up and downs. So then we didn't do that well. Probably in the middle out of like 8 teams, we are like a 4th or 5th or even 6th. I just try to forget about it, right? And then after like the really challenging like 2024, we finally figure out how to achieve fully autonomy on Flappy. So then we actually kind of bounce back this year in April. So we are actually the 3rd place, right? So it's actually a very fun, long journey. And this is the venue we have at George Mason. So like we have 3 goals on this side, 3 goals on the other side, and we keep all the blimp inside of the big nest. And also thanks for ONR for a dual grant to allow us to do that again. Okay, and then let me show you how we did it, right? So then the first research direction, because we have this big design constraint. So the first direction is we try to think about what is the minimal necessary design we really want on the blimp, because we want to save, we want to push to the limit to that direction, right? So the end product is actually led by my student Youjang. So we actually come up with this design. So we actually put the 2 balloon that exactly that size. So if you can raise it up, right? So we put 2 balloons, one in front, one at the back. And then this 2 balloon together is actually using the exactly same configuration as we have here. So we have 2 propellers with servo motor, right? So we try to minimize the propeller and also motor number. So 2 propellers here, and we have to put a cage beneath it to capture more gimbal. And then at the end of the cage, we put a propeller. So this is our shooting mechanism. So when we are ready to shoot out, you just actually generate a jet of wind by rotating the propeller, and then it will able to blow the blimp out, right? So this is the design. So then this is actually a much clear configuration. So 2 propeller on this side and then one on the back. And this is a list of weight and also cost, right? So you can see this number is about 100 grams. That's not counting this like cage structure. But with the cage, we can do this under 200 grams, right? Around 200 grams. And the cost of this is very small, very low. So this actually enabled me to do some exciting outreach work I will briefly talk about later. Okay, and then to control, we actually use the exactly same motion primitives because that's already efficient enough. So we put one onboard camera on the blimp, and then it's able to detect like a gimbal or try to identify whether this is a goal, whether this is a gimbal. So then the control strategy is same. We're just trying to control the corresponding target I'm looking for at one specific area of my camera frame, not necessarily the center, right? So you need to like do a lot of fine tuning to put it at the perfect location such that the gimbal is able to go see. But then we are able to do that. And then also the software is also minimal but necessary, right? So we have 4 stages. The first stage at the beginning, if I don't see anything, I'm just going to do ball searching, because the first step is you need to capture a ball, right? The ball searching, and then if I detect the ball, yeah, and also like the challenge is that there's no direct localization. So the one during searching our solution is that we use the goal as a reference, right? And also we put a barometer on board, which is very light, cheap to measure the altitude. Okay, and then if we get the ball, we capture the ball, move forward, and then if we capture a ball, try to search for the goal and then score, right? So this is very simple, but also efficient state machine logic. Okay, so then let's see how we do. I don't know when. You can see, you can hear me yelling on the background because I want to show you the excitement, right? So this guy is trying to score now, fully autonomously. Yeah, we got 1 in. And then another one is actually we need to swap color. So that's another constraint we have on the competition. So one day you play blue team, one day you play red team, right? So then we need to make sure our design is also modular. Okay, and due to the sake of time, let's move on to the second direction we try to do is we try to invent like a unique and new locomotion. So this is a flappy work, and this is actually done together with my great colleague from mechanical engineering. I need mechanical engineering help, right? Because this is designing a lot of hardware, try to study the aerodynamics. So we actually have a family of flappy agents. So the one you see today is this one. And also our team will have a great artist to draw this out. It's actually mimicking this sea creature, right? And then like still like runs the iteration, we eventually actually have one agent, which is called Georgie, that is able to score fully autonomous. Okay. So then again, a little bit more detail about the flappy agent you see. So it has two wings, right? So then this is the only actuation that allows you to fly forward. But the good thing about Blimps is because it can glide, right? So it has this like nice, elegant streaming behavior, so you can glide. And also, if we want to control yaw, you just have one side flapping, right? Another side stop, and this is how we are able to fly. And then also, if we want to actually have a sharper turn, we can use the tail rudder to help us to turn. All right, and then climbing up, yes, we can also use the same tail, but pitch up, right? So this will also allow us to pitch up and also pitch down. The last thing I want to show is very cool. So if we have a bigger tail, actually we're able to do this trick. So you fly in a circle because the pitch angle is much sharper, right? So then we can do this. So this is it's cool. Yeah. So then like what, and also the scientific, a little bit nice scientific result we find is actually we try to compare. So what's the difference between flapping wing and the propeller, right? So we find out the flapping wing is like much more energy efficient. It's because like the flap will allow you to glide for a long time, right? So the test we did is that we actually use a load cell, which is able to measure the thrust. And then to test the duration, we compare like different shapes of wings and also have the combination, compare this with different propeller to motor combination. So the test is that we use exactly the same battery, fully charged. We just let it fly as long as possible. So then we find out that the flappy result is here, meaning that the flappy can only fly slower, right? So maximum speed is here, right? About 1 meter per second. Propeller can achieve much faster motion, but then the trade-off is actually it has less duration, right? So flappy can actually like outperform like duration-wise than all the propeller, right? So this is one of the nice benefit, and also the design and this result is in one of our conference paper published last year, right? And then later flappy is just for showcase, right? So for demo. Later, we finally find out how we are able to achieve a fully autonomy for our agent, which is called Georgie. So Georgie is bigger. So this envelope is customized by our own student because we want to have a bigger volume to carry a little bit more. Meanwhile, we still want to make it aerodynamic efficient. So our student actually handmade this whole envelope. So the trick the Georgie can do is because now it's big, only have the tail won't be enough to change the pitch angle. So what we do is actually at the belly, right, beneath it, we actually put a very long rail and then use this gear system to move the CG, so move the heaviest part, which is a battery, to the from the head to the tail, right? So then by moving the battery around, this is how we are able to change the CG, right? So this is actually very forward, so then the blimp is able to pitch down. And if we move it to the tail, it's able to pitch up, right? So then, and also using what we have on board, right? Again, because I don't want to introduce any more weight or any more actuation. So this is actually kind of like a smart design we do. Okay, and then this video is so cool. It's because this is the only penalty shooting round we ever have in our blimp competition. It's because some other team violate some rules against Georgie. So then Georgia has 5 minutes by itself, and then try to score as much as it can, fully autonomously. Okay, so then let's see one round. So it's, when we shoot a video, it's already captured 2 balls autonomously, and then we can see it glides through.
Let's go.
And this is the yelling by my colleague, Dr. Dago Shoshika, because, yeah. And during that round, we scored like a 3 fully autonomous goals. So we got 30 points out of the penalty shooting round. Yeah, so that's good. That's good enough, right? And this is actually a joint work between 2 ME students and also my student Youjang. So I really like this is because this truly shows actually a joint team effort. So Youjang help a lot with like the autonomy and also software design. Meanwhile, the 2 ME students actually work a lot on the mechanical design. Okay. And then the second part, so like I want to quickly talk about this is also with all the blimp, right, flying around, we really want to think about, okay, can we push to the direction, how they are able to collaborate? Okay, so then we try to actually think about, and also I want it to be fully distributed because again, we only have crappy communication, right? So it will actually better to help to let them actually collaborate distributedly. So the strategy we use is actually like one strategy established by my previous colleague, Wenchen Wu. So she has this like a speeding up, slowing down strategy. So what it does is mimicking fish behavior, right? So like this strategy is very simple. So if I actually have a local measurement, so if my measurement is small, so the forward speed is just proportional to your current measurement, okay? So what we do is if my target is a goal, if I'm closer, then I will slow down. Then if this side is further away, I will speed up. So try to catch up. So eventually I'm able to converge to the like the target. So then let's just see how it will work out. So this 2 backbone agent, our main scoring agent, it's actually trying to like have an estimation of distance based on the like a camera measurement, right? So if it's bigger, I'm closer, so I slow down proportionally. If I'm further away, I also like try to catch up faster. So you can see the tracking behavior is very well. They don't communicate, even though we put a rod in here, we just want to carry a net, right? I will tell you what the net is going to be used, right? So they just try to regulate this forward speed and can actually capture, like try to follow tracking this like really nicely. Okay, and how we are going to use this in the competition is like I said, I put this rod and also the net beneath just to do a difference, right? So if I don't see any like opponent agent, so it will just try to fly forward. Once it see a target, I can use what I just showed as the tracking, right, to actually autonomously and also collaboratively approach to the goal. All right, and also to do the sake of time, so this all the theory is analyzed, right? So it's guaranteed to converge as a source seeking algorithm. So yeah, due to the sake of time, I will skip this. And this is our success defense. So we are the red team. The blue team is from our opponent, right? So using this strategy, so we take the target to be the blue agent, the color of the opponent, and they are able to capture both of them and smash them on the wall. And we leave them there like for one autonomous mode, so 5 minutes. So we are good, nice friends. So we'll let them down. Okay. Okay, and then just to show you something else, like why just using vertical net, right? I can also use like a gripper. So this is one work done by my senior design team. So I just give them this result. I don't want this like a sweeping behavior. I want a giant gripper, right? So they are able to come up with this. So they use actually the leg of the gripper is actually just pulled by string. So if they release the string, the finger will like naturally force down by gravity, right? Again, so we've tried to follow the philosophy that minimal but necessary, right? So then using gravity, you can force down. And they use like a PID controller. So they put down-looking camera here, just try to seek for the opponent agent again. So if they see an opponent agent, they will try fly down and grab it, right? So also sometimes it backfire us, capture our flappy. But we do have some successful defense during the competition, right? So fly up is very big, right? So you can capture me. And I think one of the agent actually fly down. And also we put two baits, which is a purple LED light and also green LED light, just to trick other agent to fly in and thinking this as a game. Yeah. Yeah, so I think it's able to capture this this blue guy and then grab it and keep it there, right? So this is a fun. So the last fun project, which is also a recent design, right? So we want to extend the flappy, which now we try to like using the like a linkage and also linkage mechanism. So what it does is that like our ME teams try to design this like a phase difference between each linkage by 60-degree difference. So then what we can do is by just using one motor, it's able to actually generate this behavior, right? This wavy behavior. And this is how we call this Annie. So how Annie is able to fly during the competition, right? It's a good thing to see. Currently it's useless. So it's eye candy to attract all of us. Okay, so then I'm going to skip this part. And also, like to make it more generally, like the more general application, we also try to create the digital twin to actually enable something like a reinforcement learning. So this is actually a digital twin. We developed this in Mojoko. So with this, we can directly import our gondola CAD design inside of it, and also we can actually take the onboard camera. Okay, and then this is just a very quick demonstration of what Youjang did. So he's able to actually use reinforcement learning enabled like controller to control this guy. And what it learns is actually it learns the trick, try to have one side taking care of altitude and one side to do turning. So this is directly, it's not following the 3 motion primitives we defined, but it learns to do this trick. So with the digital twin, now we can actually use also like the reinforcement learning or other learning method to actually help us to design the content. Okay, so I will quickly do this. So because Blimp is so safe, right? And also it's encouraging kids to actually participate. So actually this summer, I took the effort to bring the Blimp competition to younger kids, right? So we actually launched the first robotic Blimp competition for middle and also high school students. So it's aiming for grade 8 to grade 12. So this year, this is the first time we try it. So we actually have more than 50 students to participate. And we provide them with the basic Blimp kit. And also one of the benefit is it's very low cost. So each kit will only cost $180. So then like the training we provide is we have 8 weeks of training. So we provide them written down document, the start guidance and with the basic kit. And also we organize several in-person tutorial sessions and 1 day of competition. And we are able to attract some like government officials, for example, the Maryland Secretary of State, now Miss Susan Lee come, and also Maryland State like a senator also come to support the event, right? So I want to show you one team's video, which I really like to show their whole path of how they what they get through from the competition. So they use, this is our basic kit, and also Youjang provide this in-person tutorial, help them to solve problems in our lab. And then they can just build upon the basic kit, right? So even though they have no experience with programming, no experience with mechanical, they can still use just daily material, try to test the Blimp, right? Design the capturing mechanism, use trash bags to design the wings to make it more air like dynamically efficient. And this is actually showing they use the capturing mechanism they design to capture the game ball. And they also learn how to do the basic programming, sometimes to change some program. Even though we actually provide the programming, the code for them, they are able to access to fine tune the controller parameters, trying to fine tune. And also they also took the effort to rent a basketball court and do practice, right? So this really shows how motivated the students are and also how engaged they want to do the competition well. And this is showing actually what's happened on the competition day. So we have 1 day full competition, and also to encourage them certificate medals, right? So during the competition, like parents and the student work really close together. And this is the same thing. So they actually be able to do well. So they are the 3rd place out of 8 teams. So we play this competition for all the days, and also we are able to attract a lot of audience to attend, right? So this actually make me very happy, because then this shows how an easy and also accessible platform is able to encourage and also promote STEAM education to the younger kid, right? And the parents like it. So parents actually is able to see our effort. So she's quoting actually the Hindenburg airship, which is the airship I talked at the beginning. So the one that blows up, right? Then they are able to appreciate how difficult it is. And then the second one I really like is it's actually from a participating student. So he said, with each failure, we learn something new. And we try to fix it with new approaches. And then step by step, this is how they learn. So they really learn to bounce back from the failure and also learn something new through the hands-on project. And then this is other outreach. We do demo in IROS and also AIMS. And I also showcase this to elementary school students. And also this is the indoor tutorial. And also nowadays we are helping Mason to recruit our undergraduate student. Okay, so this is the last slide to actually wrap it up. And this is also the celebration. They like to live celebration. So let's rewatch this again. So this is also my senior design team. They just like this action. Okay, so I want to wrap up a blimp. As we know, it's safe, right? So it's long duration. It's actually low cost at its benefit. But I also want to share some insight about what are the design challenges, and also meanwhile the research opportunities. So definitely we need to improve on the modeling and the control, right? So and also we as several teams participating, we can only design and also model to what we have today, right? So there are more chances to design better control. And also another important question is how to better overcome and leverage this external disturbance, right? The wind, are we able to leverage it instead of fighting against it? That's a big problem that I'm trying to work on. And also how to deal with time-varying parameter. Because helium, if you have a temperature change, so then buoyancy will dramatically change, right? So that's another problem. Can we actually adaptively design a control to compensate for that? And also last of all, remember everything needs to be on board. And if we want this to be miniature as that one, the limitation is 120 grams. So that's a big challenge, right? So that's actually end my talk. So I would just want to thank my collaborator and also my brilliant students, and also thanks to the funding agency, and also thank ICON to invite me to actually share our work. Thank you so much.
Thank you. Thank you.
This is perhaps the first icon seminar with live demo. Thank you very much,
Thank you,
Ningshi, for very nicely agreed to bring students here, set up a live demo. Thank you very much for all this. So we're planning to have maybe 2 or 3 questions, and then students could interact with the Dr.
Or if you want to fly blimps, feel free.
Yeah, exactly.
Yeah.
Maybe we have 2 or 3 quick questions, and then freely interact with Dr. Any question? Zoran.
Thank you for your talk. It was so cool. I took, I don't know, 5 different videos and I sent it to my students already. I'm just curious, how do you transport this whole thing from George Mason? Do you have to refill that here, or?
Yeah. So I actually borrowed a helium tank from Dr. Diane.
Oh.
Randai, yeah. So we can do actually to buy portable helium, which you can directly buy it from Walmart. And then everything needs to actually be reassembled. So what we do is we just bring the envelope and then reassemble everything.
Okay.
Yeah.
So I'm curious, does it have to be helium? I mean, if say you use some other type of gas.
So light the air, gas, you cannot use hydrogen indoor because it's, yeah. So helium is actually the safest
Yeah.
one, yeah.
Okay.
Yeah.
So right now, it seems like you guys have like a fixed amount of helium in the balloon,
Mhm.
the buoyancy stays fixed. Do you guys have plans to like add a dynamic buoyancy, have it like pump in helium from like a source?
Yeah, so that's a very good question, right? We try to actually change the shape.
Okay.
Yeah, because buoyancy is actually the air displacement, right? So you replace the air, this volume of air with lighter than air gas, right? So if you try to compress it, it actually can change the buoyancy. But we had this idea. The reason why we were not so successful is because the Mylar envelope we use, actually it has like very minimal tolerancy, because if you squeeze it, fine, but if I try to inflate this with like completely full, if you squeeze it, it will just, right, it will start leaking. It won't explode, but it will start leaking. So another material you can think about is maybe like a rubber, it's a latex material, so it can actually be stretchable. So, but then latex is much heavier, so then the material itself is heavier. So again, it's a trade-off, right? So which material you use at a design stage. Yeah, but that's actually a very good, right? Because then you can do a glider, right? Yeah, change the buoyancy, yeah. Any other questions? Yeah.
So the reinforcement learning based algorithm,
Mhm.
what is the overall algorithm framework you're using?
So like, do you want to talk about it?
What's the question?
The reinforcement learning, yeah.
Oh, it was just, PPO, proximity policy optimization with reward function being was minimize the distance to the goal. So the stick over there is basically.
Yeah, this is a waypoint.
Yeah, the waypoint, and you just want to minimize the distance, and you could choose any input.
Okay, I think we could save some time for, students who are welcome to stay to, ask questions, Dr. Ningshi Yao, or play with the blank or interact with the student, okay?
Yeah.
Thank you very much. Ian.
Yeah, thank you.
It's just like. Oh, yeah.